In this video, we're going to be looking at the multiplication principle. So for this video and the next few videos, we're going to be asking how many ways can something happen? And this counting of the number of ways to do something is going to set us up for probability in Chapter 4. Here's the main rule that we're going to be using in this video. The multiplication principle says, when performing a sequence of tasks, the number of possibilities is multiplied. So let's look at a quick example to understand what this is saying. Suppose we have 3 towns, A, B, and C. There are 6 different routes between A and B, and 2 different routes between B and C. If we ask how many possible routes are there from A to C, then we're performing a sequence of tasks. So to calculate this, we're first going to calculate the number of routes from A to B, and then the multiplication principle tells us to multiply by the number of routes from B to C. So you calculate number of ways to do the first thing, and then multiply that by number of ways to make the second choice. So in this case, the answer would be 6 times 2 equals 12. 12 possible routes from A to C. So the way to get comfortable with these counting problems is just to do a wide variety of examples. So throughout this video, we're going to see a bunch of different contexts where we can apply the multiplication principle. We want to figure out how many possible outcomes are there if we toss a coin 4 times. So what we care about here is the sequence of heads or tails. So let's just write down an example of what some of the possible outcomes would be. So you could have 4 heads in a row. You could have tails, heads, heads, tails. So we're tossing this coin 4 times and just keeping track of whether we get heads or tails on each toss. So we're asking, if we wrote down all the possibilities here, how many possibilities would be in this list? Well, let's use the multiplication principle to figure it out. The sequence of choices that we're making here is what's happening on each toss. So let's ask, what is the number of options for the first toss? And that first toss can either be heads, which we'll write as capital H, or it can be tails, which we'll write as capital T. So that looks like 2 options for the first toss. And then our second choice is going to be what's happening on the second toss. And then there will be a third toss, and then there will be a fourth toss. So whenever you find yourself saying, and then, that means you're doing a sequence of activities, and we're just going to multiply the number of possibilities at each stage. So there are 2 options for what the second toss could be, either heads or tails, 2 options for the third toss, and 2 options for the fourth toss. So we're just going 2 times 2 times 2 times 2 equals 16. And that's our final answer. If you were to write out all the possibilities, you would have 16 possibilities in this list. So now let's ask, how many 6-digit palindromes are there? Well, first thing we should do is talk about this word palindrome. So palindrome is a word or a number that reads the same forwards as backwards. So if we're talking about 6-digit palindromes, an example would be something like 784 487. So once we've decided the first 3 numbers, the last 3 are forced because they're just repeating the first 3 numbers but in the backwards order. So another one would be something like 932 239. So those would be 6-digit palindromes. And you could have repeated digits. So you could have 422 224, for example, or 111 111. All of those are 6-digit palindromes. Something that would be excluded would be a number that starts with 0. So 019910 is a palindrome, but it's actually not considered to be 6 digits because when we write numbers, we usually drop leading zeros. So this number would be more naturally written 19910, and therefore it's not 6 digits long. So what we're realizing here is that the first digit can't be 0. Second and third digits can be anything we like, and then after that, the last 3 digits are going to be forced by the decision that we've already made. So now that we know what these 6-digit palindromes look like, the question is, how many of them are there? So let's see if we can use the multiplication principle to answer the question. So we'll ask, what is the number of choices for the first digit? And then we're going to multiply by the number of choices for the second digit. And instead of saying number of choices for second digit, I'm just going to write second digit. And it'll be implied that we're talking about the number of choices for that digit. And then we have to think about the third digit, the fourth digit, the fifth digit, and the sixth digit. So at each stage, we're going to be multiplying because we're thinking about the first digit and then the second digit. The and then is prompting us to multiply. Okay, so we're going to have this big product here, and our goal is just to figure out how many options we have. So for the first digit, we've said that first digit should not be 0, but it could be anything 1 through 9. So there are 9 choices for the first digit. For the second digit, it could be anything 0 through 9. So that's actually 10 different options there. And similarly for the third digit, 10 different options. Okay, now from here, this is where things get interesting. Because we're talking about palindromes, once we've decided our first 3 digits, let's look up at the top of the screen here. Once we decide 784, then we have no choice, or really better to say no freedom on how to choose the last 3 digits. There's actually just one way to choose the 4th digit, 5th digit, and 6th digit because we're forced to choose the digit that makes this number read the same forwards as backwards. So when you say you have no choice, you're really saying you have no freedom, and properly we should say, that means we have exactly one choice for how to do this. We're forced to do something. There's only one way to do it. So 1 times 1 times 1. And then multiply these numbers out, and that's going to give us our answer. So I'll just say equals, final answer down here, 900 ways, or 900 different 6-digit palindromes. Now we'd like to figure out how many 5-digit passcodes using digits 0 through 9 are there if adjacent digits can't be the same. When we say adjacent digits, we mean digits that are right next to each other. So an example of what would be allowed, you could do something like 98723. That's 5 digits using digits 0 through 9. You could do something like 98283. That's fine. The 8s aren't touching each other. But what you're not allowed to have is something like 98823. We've said adjacent digits can't be the same. So what you're not allowed to have is the same number written side by side. So the whole secret to this type of problem is to see if we can break it down into a sequence of choices. So let's ask how many options are there for the first digit, and then we can talk how many options for the second, third, fourth, and fifth digits. So the first digit can be anything 0 through 9. So that means there are 10 options for the first digit. For the second option, it's a little different because the second option has to be different than the previous one. So I'm going to add some detail here. Let's talk about the second digit. It can be 0 through 9, but different than the first digit. So we don't know right now what the first digit is, but we know that whatever it is, that's removed from the pool of possibilities. So there are no longer 10 possibilities. There are only 9 options for the second digit. And same kind of reasoning tells us that there are going to be 9 options for the third digit. So the third digit, again, can be anything 0 through 9, but it has to be different than whatever digit we chose for the second position. Similarly, the fourth digit, 9 options, and 9 options for the fifth digit. So I'll write a bit more detail for this fifth digit. It can be anything 0 through 9, but it has to be different than the fourth. And the multiplication principle tells us that we are just going to multiply the number of choices for each of the digits, because we're just making a sequence of choices here. So final answer coming up, if we go 10 times 9 times 9 times 9 times 9, 65,610 possible 5-digit passcodes using digits 0 through 9 with adjacent digits not being the same. So now we want to figure out how many Canadian postal codes are there, and we're going to assume that there are no restrictions. So Canadian postal code looks like this. Let's write down an example. So it's got a letter, then a number, then a letter, then a number, then a letter, then a number. Now in practice, some Canadian postal codes are not used. For example, I believe the letter O is not used, and there may be some other restrictions as well. But let's forget about those restrictions, and let's just say the pattern is letter, number, letter, number, letter, number, and we're going to count the number of possibilities. So let's turn this into a sequence of choices by just asking how many options are there for the first symbol. So when we write down first symbol, we're really saying what is the number of choices for the first symbol. Then we'll ask number of choices for the second symbol, then the third, then the fourth, the fifth, and the sixth. And that way we're breaking the problem down into manageable pieces. Because we're doing a sequence of choices or a sequence of activities, we are just going to multiply the results at each stage. All right, now some of these are going to be letters, some are going to be numbers. So let's add some detail here. So the first one is going to be a letter, so is the third one, and so is the fifth one. And let's assume all letters A through Z are allowed, because we said in the question there are no restrictions. Second, fourth, and sixth symbols are going to be numbers. And let's again assume there's going to be no restrictions, so we can use anything 0 through 9. All right, so let's think about our possibilities. So number of choices for the first letter would be 26, and that would be the same for the third position and for the fifth position. 26 letters in the alphabet. And then for the numbers, we're going to go 0 through 9. So that's 10 options for the second, fourth, and sixth symbol. And then to get our answer, we're just going to multiply these numbers together. Quite a big number of possibilities for how many Canadian postal codes there could be. Let's figure out how many 10-digit phone numbers have area codes 250, 778, or 236, such that the last 7 digits aren't all zeros. Well, let's see if we can break this up into a sequence of choices. We've got the phone number and the area code to deal with. So let's talk about the phone numbers first. Let's talk about the number of 7-digit phone numbers. And we'll first do this with no restrictions, and then we will take into account the fact that we want not all zeros. We'll take that into account later. All right, so 7-digit phone number just involves making a choice of 7 numbers, and for each digit there would be 10 possibilities for what that digit could be. It could be anything 0 through 9. So we'd be going 10 times 10 times 10. If you get bored of writing that, you can just go ... times 10. And so a faster way to write that would be 10 to the power 7. So that's the number of 7-digit phone numbers with no restrictions. But we were told in the question, we want to avoid the possibility of all zeros. So we're just removing one of the possibilities, and that is the possibility that your phone number is 0000000. So the number of 7-digit phone numbers other than that single number that we want to avoid is 10 to the 7 minus 1. So let's put an equal sign on here. So let's go through our logic so far. We said the number of 7-digit phone numbers with no restrictions is equal to 10 to the 7. Number of, let's say, desirable 7-digit phone numbers is equal to 10 to the 7 minus 1. Okay, now we need to think about one more choice, which is the area codes. Number of possible area codes. We were given in the question, the options were 250, 778, or 236. So So we can see that here. If we're just counting the number of area codes, that's 3. 3 options for what the area codes could be. So what we're trying to calculate here is the number of allowable 10-digit phone numbers. Well, we've said there are 3 options for the area code, and then we figured out that there were 10 to the 7 minus 1 options for what the last 7 digits would be, just avoiding that number that's all zeros. And the brackets here are really important to make sure that the 3 gets multiplied by the 10 to the 7 and the minus 1. So if you wanted to turn that into an explicit number, we could put that into our calculator. We get 29,999,997 allowable 10-digit phone numbers. Let's figure out how many ways are there to arrange 7 books on a shelf from left to right. So we can imagine that we're actually going to be laying these 7 books out like this. So we want all 7 books to go into a row, and the choice that we have is just what order to put them in. So let's think about what the leftmost book could be. Specifically, let's talk about the number of choices for this first book. And then we'll think about the number of choices for the second book. So we're going to do a sequence of choices. Therefore, we're doing multiplication across here. And then the last number here is going to represent the number of choices for the 7th book. So if we've got 7 books to arrange, there would be 7 options or 7 choices for what that first book could be. But once we've placed that book, there are now only 6 books to choose from. So the number of choices for the second book would be 6. Now we've placed those first 2 books. And so let's imagine we've got 5 more books that we're holding, 5 options for the next book, and then 4 options, then 3 options, then 2 options. And by the time you get to the last book, you are forced to place that last book in the rightmost position. Whenever you're forced to do something, that means there's one way to do it. So we could then grab our calculator and figure out that our total number of ways to arrange these 7 books is 5,040 possible ways. Okay, let's say you're working at a company and you are on a hiring committee. Let's say 10 people interview for a job. Let's figure out how many ways there are to choose the best and second best candidates. So maybe your hiring committee is just trying to make a short list, and you want to come up with 2 people, one who's ranked first and one who's ranked second. So here what we're doing is we're making 2 choices. We're figuring out who's best and who's second best. The word "and" is prompting us to multiply. And specifically what we're going to put in this box here is the number of choices for the best candidate, so whoever is ranked first, and then the number of choices for the second best. So if 10 people interview for a job, then in theory there are 10 options for who could be ranked best. But then once someone has been selected as best, see, they're out of the pool of candidates for second best. So there are now only 9 options for who could be ranked second best. So 10 times 9 gives us 90 possible different ways of choosing a best and second best candidate. So continuing with the same problem, 10 people have interviewed for a job. Let's figure out the number of ways to rank them first through 10th. So a couple of things to notice here. First, I think really important thing to notice is that this problem is basically the same type of problem as arranging books on a shelf. Because you're thinking of placing these 10 people, you could actually imagine standing them in line like this. You'd have a line of 10 people, and you're just essentially saying, okay, whoever we rank first will be here, and whoever we rank 10th will be here. So it's really the same problem as arranging books on a shelf. It's just worded slightly differently. Second thing to notice is this is just going to be a very big number. So if you were actually on this hiring committee, you definitely would not want to sit around a table and try to rank people 1st through 10th if you were having to agree with some of your colleagues, because there are just so many possibilities to choose from, and it's unlikely that 2 different people would agree on the same ranking. So probably better to do something more like option A, where you maybe just pick your best and second best candidates. So let's figure out exactly what this number looks like. So if we've got 10 people who interview, in theory, there would be 10 choices for who would be best. And then we're multiplying because we're making this sequence of choices. There would be just 9 options for who could be ranked second best, because once you've assigned someone as being first, they're out of the pool. There are now only 9 people to choose from for who could be second best. Okay, then when we get to third, there are only 8 people to choose from, so 8 possibilities there. And we can sort of see the pattern at this point that each time you've got 1 fewer person to choose from. So 7 options, then 6 options, then 5, then 4, then 3, then 2. Then by the time we get to the last person, they're forced to be ranked last. So that means just 1 choice there. All right, so you could try typing this into your calculator. It is going to come out to 3,628,800 possibilities. So just by taking 10 objects and asking to arrange them in order, you are getting quite a large number of possible ways to do that. That's one big takeaway from this problem. So here's our last problem for the video. We want to ask how many 3-letter words can be formed from the symbols A, B, C if repetition is allowed. Well, notice that we have this word words here in quotes. What that means is that these don't have to be true English words. We're just talking about putting 3 of our symbols together. So it could be something like ABC, CAB, CBA, etc. But also notice we're told repetition is allowed. So we're allowed to use the same symbol more than once. We could have things like AAA, we could have BBC. So let's figure out how we can use the multiplication principle to break this problem down. I would just think about, what do we want our first letter to be? And then what do we want our second letter to be? And then what do we want our third letter to be? And specifically, we're talking number of choices or number of options for the first letter. So we'll figure out the number of possibilities for the first letter, multiply it by the number of possibilities for the second, and then multiply by the number of possibilities for the third. So I'm just going to write these multiplication symbols in the correct place. Okay, so number of choices for the first letter, well, it could be A, B, or C. So that would be 3 options there. For the second letter, there's no restriction. It can still be A, B, or C. So 3 options again. And again, 3 options for what that third letter can be. So we're just getting 3 times 3 times 3, which is 27. But now let's change this, and let's say in part B, repetition is not allowed. Okay, so now we've got these 3 letters, A, B, and C, and we're really just deciding the order in which to write them down. So you could have ABC, you could have ACB, you could have CBA, etc. It's a pretty small list of possibilities, so you may be able to figure it out just by writing out all the possibilities. But let's see if we can use the multiplication principle to figure it out. So we would first think about what the first letter could be, and then we could think about the second letter and the third letter. And specifically what we're doing is we're thinking about the number of options or the number of possibilities for the first letter. And then we'll multiply that by the number of possibilities for the second letter, and then multiply that by the number of possibilities for the third letter. So there would be 3 options for what the first letter could be. It could be A, B, or C. But once we've decided on that first letter, now we only have 2 letters to choose from. So 2 options for the second letter, and then 1 final option, which is forced for the third letter. So 6 possibilities in total. So it's good to notice that part B here, this is the same type of problem as arranging 7 books on a shelf. And it's the same type of problem as ranking 10 interview candidates from best to worst. It's really the same problem, just worded differently. And of course, with slightly different numbers involved, because in the book problem, we were arranging 7 books. In the interview problem, we were ranking 10 candidates. So we'll see some more counting techniques in our next video. Thanks for watching.